That brings us to section 13.3. We'll talk about predictor significance and the logic of hypothesis testing for different coefficients in a multi-regression model is exactly the same as it is in simple regression analysis. So we'll calculate t-statistics, so the computer will do this for us. We're testing it to see if the estimated coefficient, lowercase b, sub j, where j is our index for the number for the regressor, j equals 1 to k regressors. We're going to test to see if the b, the coefficient, is different from 0. So in the numerator of the t-statistic, we've got b minus 0, and we divide that by the standard error of the coefficient estimate. So in general, if the coefficient estimate is greater than 2 times the standard error, which is our measure of the spread or the function of the variance of the coefficient, then we have a good feeling about whether it is statistically significant or not. And the degrees of freedom for this t-test is equal to n minus k minus 1, but generally we think about the critical values for the t in regression analysis with large samples at the z-score cutoffs. So at the alpha equals 0.05 or 95% confidence level, the t critical value is 1.96. So the standard errors in a simple regression, we define those as, the notation was S sub b, and 1 because we had a single regressor in a simple regression, and it depended on the standard error of the regression and the sum of the squared differences of the regressor variable from its mean. Okay, and then the standard error of the regression is the sum of squared errors of the individual dependent variables from their predicted level, okay, adjusted for the degrees of freedom, and SS sub XX was our notation for the sum of squared deviations from the mean. Okay, and so if you take the square root of both of those, then we get the square root of the mean squared error in the numerator. Okay, and then that is the square root of the mean squared error divided by the sum of squared deviations from the mean for the x variable. In a multiple regression, the formula is similar. Okay, except the notation we'll use is now just S sub j, since we have more than one regressors, and that's equal to the mean squared error multiplied by the sum of squared deviations from the mean for the jth independent variable, and then we multiply that by 1 minus r sub j squared, where r sub j squared is the coefficient of determination, or the r squared statistic, when predictor j is regressed against all of the other predictors. Okay, so think about that. To calculate the standard error for each regressor variable, we would need to run another multiple regression where the x variable, say the number, say the square foot, is the dependent variable, and then we regress that on variables like lot size and the number of bathrooms. And their r squared for that statistic would go into this calculation. So that is very tedious, and it's something, so this standard error is something that the computer is going to do for us. So this calculation is even more tedious than we found the standard error calculation in chapter 12. Okay, so in terms of statistical significance, think about what that means for your linear model. So here we have a theoretical model where y depends on x1, x2, x3. We've got an error term out here. Then we estimate the model, and we have that results in an empirical model where the coefficient estimates are B0, B1, B2, and B3. So imagine B0, B1, and B3 are all statistically different from 0. Statistically significant. Imagine that your estimated B2 is not statistically significant, not different from 0. Okay, so conceptually, your model now looks like this. Y equals B0 plus B1 times X1 plus 0 times X2 plus B3 times X3. Okay, so then the question is, well, what should you do with that model? Should you report those results? Should that be your final model? Or, since the effect of X2 on Y doesn't matter, should you drop the variable X2 and re-estimate the model? Okay, so you got to use some judgment. Okay, there's going to be a lot of judgment when we're doing multiple regression analysis. Okay, so one thing to think of, if X2 is theoretically important, then it should not be dropped from the model. So if Y is home sales and X2 is location, a bad location, then you might want to continue to include the X2 variable in the model, because it says that that location really isn't bad. And so that it tells you that a holding constant location, we've got an unbiased estimate of square foot and something else. Okay, now if X2 is not theoretically important, it turns out it might be a trivial variable or what's called an irrelevant control variable, then feel free to drop that variable from the model. Okay, and then we can also construct confidence intervals for Y, the dependent variable, and we do this in a similar way that we did in chapter 12, except now the standard error for the regression is adjusted for the number of regressors. Okay, in simple regression, K was equal to 1, so n minus 1 minus 1 is n minus 2. Okay, so the book calls these are, in chapter 13, it calls these approximate confidence intervals. In chapter 12, this style confidence interval is called the quick confidence interval. And then in chapter 13, the quick confidence intervals replaces 1.96 with 2. So that's confusing as you go from chapter 12 to 13. But we'll go with the approximate confidence intervals, where if we're doing 95% confidence intervals, the t critical value is 1.96. And we'll save these, what chapter 13 calls these quick confidence intervals, where you place 1.96 with 2 for the type that you might do in your head or during the meeting with where you're making a presentation. You have to think quickly on your feet. So the confidence intervals for a dependent variable Y, you take the predicted value of Y, and then you add and subtract 1.96 multiplied by the standard error divided by the square root of n. Okay, so these are confidence intervals. Chapter 13 also talks about prediction intervals, and we're not going to worry about those anymore because the data that we have, those prediction intervals are always going to be so wide that they include 0. So we're going to be thinking about confidence intervals.